Hi there, I'm Rebecca Weaver. This is Chapter 6, and we are looking at the definite integral today. Section 6.1 is antidifferentiation, so let's look at what that definition is. So for antidifferentiation, the antiderivative, it's the process of determining f of x given f prime of x. That means we're going to be going backwards. We're going to have the derivative, and we have to determine the original function. So if f prime is 2x, going backwards, we would say that the original function had to have been x squared. Now notice that that could have been x squared plus 5 or x squared plus 4 or whatever, because that constant you could have had that and taken the derivative of a constant as 0. So there's a number of answers to this, and we'll figure out what we're going to do with that constant in just a minute. The definition of antiderivative: suppose that f of x is a given function and f of x is a function having f of x as its derivative. Now that was capital F of x. That is f prime of x equals f of x. And we call capital F of x an antiderivative of f of x. So, for example, we're to find all the antiderivatives of the given function, and our function that we are given is f of x equals 9x to the 8th. Now, the derivative of x to the 9th is exactly 9x to the 8th. Therefore, x to the 9th is an antiderivative of 9x to the 8th, but now so is x to the 9th plus 5, like what we were talking about before with that constant, or x to the 9th minus 17.2, or whatever constant you want to put. Now it turns out that all the derivatives of f of x are of the form x to the 9th plus some constant c, and we just use a capital C for that, as we're going to see. And the derivative of a constant function is 0. So for Theorem 1, suppose that f of x is a continuous function on an interval I, and if capital F1 of x and capital F2 of x are two antiderivatives of f of x, then capital F1 of x and capital F2 of x differ by a constant on I, that interval. In other words, there's a constant c such that F2 of x and F1 of x plus c for all, or they're equal for all x in that interval. Now Theorem 2 says is if capital F prime of x equals 0 for all x in interval I, then there's a constant such that capital F of x equals c for all x in I. Another definition of what we're going to call the indefinite integral, and this is how we're going to write this. This is like an elongated s, because the integral we're going to find out later is an infinite sum, so it's a big S for sum is the way I kind of look at it. So use that big elongated curve there. That's the integral. Suppose that f of x is a function whose antiderivatives are capital F of x plus c. Now, the standard way to express this fact is to write the integral of f of x with respect to x, or f of x dx. That's what that dx means, is with respect to x, equals capital F of x plus c. And that with respect to dx will be important later on when you're integrating with respect to 2 or 3 different variables at once. So the symbol, that elongated s, is called an integral sign. The entire notation, the integral of f of x dx, is called an indefinite integral and stands for the antidifferentiation of the function f of x. So for our power rule, if we have the integral of x raised to some r dx, that's going to equal 1 over r plus 1 times x to the r plus 1 plus c, where r is not equal to -1 and r is some constant. The exponential rule says that the integral of e to the kx dx is 1 over k e to the kx plus c, where k is not 0 and it's some constant. For our log rule, the integral of 1 over x dx is the natural log, and since we can't take the natural log of negatives, we have to put the absolute value symbols in there to say, hey, this has got to be positive. natural log of the absolute value of x plus c, where x is not equal to 0. Now the basic properties, we can break apart an integral if we have a sum of two functions, f of x dx, into the integral of f of x dx plus the integral of g of x dx. In our constant multiple rule, because constants are just constant multipliers, if you have the integral of k, some constant f of x dx, you can just pull that constant out and have the integral of f of x dx, where k is some constant. So let's play. Now, determine the following. We have the integral of x minus 2x squared plus 1 over 3x dx. So we have quite a few rules that we're going to follow here. So let's use these rules. We're going to first separate this into three separate integrals because we have a sum of three different things here. So with that integral of x dx, that's going to be using our power rule. With that negative 2 in front of that x squared, that's just a constant. I'm going to pull him out front. Same thing with the 1/3. So now I can use my power rules and I can use my natural log rule. And I'll end up with x squared over 2 minus 2x cubed over 3 plus 1/3 natural log of the absolute value of x plus c. And that's all there is to it. So we need to find a function f of x for which f prime of x equals x squared plus the square root of x. And they're letting us know a little additional information that f of 1 equals 3. Now we're going to use that at the very end, so don't even deal with that right now. That's just going to tell us what our constant c is. So don't play with that. So we have this unknown function f of x, and we know that his derivative is x squared plus the square root of x. So one antiderivative would be x cubed over 3 plus 2x to the 3/2 over 3 using the power rule. So by theorem 1, I can just write that down, and c is a constant. Now, what we want is a function for which f of 1 is 3, so that's going to give us our constant. So we'll plug in a 1 for x, solve it, and we'll get our c. So we'll plug in a 1 for x, and we know that that f of x is 3. So this is what it's going to look like. We're going to say 3 equals f of 1. We'll plug in that 1, and then we're going to solve it for c. And I end up with 3 equals 1 plus c. So I know that c must be 2, and our function is just going to look like x cubed over 3 plus 2x to the 3/2 over 3 plus 2. Let's do one more example here. A rock is going to be dropped from the top of a 400-foot cliff. Its velocity at time t seconds is v of t equals negative 32 t feet per second. We need to find s of t, so that's the distance, the height of the rock above the ground at time t. We need to find how long the rock's going to take to reach the ground and what its velocity will be when it hits the ground. One nice thing about it hitting the ground is I know that that height is 0. So that's a nice thing. All right, well, we know that s prime of t equals v of t, which is 32t. And we also know that s of 0 is 400. Now we're going to use that information to find the antiderivative of v of t. So we're going to take the integral of the negative 32t dt. We're going to end up with negative 16t squared plus c. And we're going to need to determine c. We're going to use that s of 0 is 400 for that. And we're going to figure out that c happens to be 400. So our antiderivative is s of t equals negative 16t squared plus 400. Now to determine how long it's going to take for the rock to reach the ground, we simply need to find the value of t for which the position of the rock is at a height of 0. Hey, that's nice. So in other words, we need to find t for when s of t equals 0. So just plugging that in, replacing s of t with 0, solving for t, dividing, taking the square root of both sides, I find that t is 5. So it's going to take 5 seconds for the rock to reach the ground. Nice. To determine the velocity of the rock when it hits the ground, we're going to need to evaluate v of 5. Hey, I just have to plug in a 5? Oh, that's nice. So the velocity of the rock as it hits the ground is 160 feet per second in the downward direction. That's what that negative sign means. All right, and that's all we have for section 6.1. I know that's a lot, so if you have any questions, you be sure and email me, and have a wonderful day. Thank you.